recording. Yep, it's all good. Beer. It's not like you can really do much about it. Beer, as in B-E-E-R, beer. Root beer. As in root beer. You're not going to make a very good hacker, aren't you? What's the password again?
Social engineering and being given the answer.
Right, because a typical hacker would just hear the word beer, and then they will automatically try all different cases, combinations, turning all the E's into threes, uppercase, lowercase combination, and stuff like that. That's at least how I think.
There's a program that does that.
Yeah, there are programs that do that, but I can lock people out after 2 minute attempts of logging in. So those programs won't help. All right, so let's go ahead and get started with this class. Any questions about the homework assignment? Because today would be a good day to ask those questions. Any questions about subtracting? Or what your homework assignment should look like? It was fun? It was easier.
It was easier.
It was easier. Subtraction is actually easier.
In the spreadsheets?
Huh?
It's easier because I already did it.
Because you already did it.
I used the and thing instead.
The end.
The and, the 2 by 2 adder. You use it. Just change the nuts.
You have to change a lot with this one. The only thing you can keep is Z0, or the result, the least significant of the result. That's the only one you can keep. Everything else is dramatically changed. Well, I guess when you turn it in, I will know how it works.
Spreadsheet makes it a lot cleaner.
Yes, the spreadsheet is definitely a very good help with all the mechanical stuff. Because once you take care of the mechanical stuff, you can then focus on just okay, which rules to apply, and so that really helps. Yeah. All right. But are there any questions about the homework assignment in terms of how things should hook up, that sort of thing? No specific questions about that? All right. Okay. So if you can think of any questions, just go ahead and ask in class, because you may not remember your questions right now. After all, it is only 9:05 in the morning. I've been awake for 3 hours, so. All right. So what we'll do today is, since we have mostly talked about, adding and subtracting already, so we are pretty much done with adding and subtracting. And it's time to move on to von Neumann machine, which is the next topic. The first part of the von Neumann machine topic really doesn't have a whole lot of stuff that you need to remember. Just stuff that you need to understand, like historically speaking, what makes the von Neumann model, significant. So what I want you to do is, well, not right now, but you can do that later on when you have time. Okay. Is to go look up, old computers. Okay, go to Wikipedia. Okay, look up the ENIAC. Look up all the older computers like Colossus. Okay, so this is a a picture of a computer that is being operated by the operators. So we'll take a look at the Colossus. As a computer, the Colossus as a computer is programmable. Okay, in other words, it's not a machine only built for doing one thing. It is programmable by changing certain things. And if you read this paragraph, it says the Colossus was reprogrammable by setting switches and plugging appropriate units together. So sometimes it would involve your rewiring, okay? Other times it's just just a regular switch, okay? And sometimes two or more Colossus computers try different possibilities simultaneously, and that is now called parallel computers, but they actually have parallel computers doing stuff at the same time. But the point is, in order to change the algorithm in a computer like a Colossus, it involves opening up the computer, rewiring the internals, okay, turning some switches, and that's how you reprogram it. One bit at a time, basically. Okay? Is that okay? So does everybody understand what it means by today's standard, right? I mean, you guys don't even have to do a single thing when your phone's apps are getting updated, right? I mean, you might turn on and say, okay, just let me know when it's time to update and I'll approve. But when you have 150 apps and 70 of them want to be updated on a daily basis, you quickly turn off that thing and go like, okay, just update yourself, okay, don't bother me. But that's not the case in the good old days. Okay, what if somebody wired the thing wrong? Okay, of the 675 wires, one is connected in the incorrect way.
You get a compiler error.
Well, the machine's not going to work correctly, right? But does it throw like exceptions? Okay. Oh, okay. We have a division by zero exception on this line of this particular program. Go fix it now. No, it just won't work, right?
Wow.
So think about debugging these things, okay? Not just the tedious amount of work that you have to do when somebody gives you a new schematic and say, okay, this is the new way of wiring this thing, and I want to come back next day and have this done, okay? And I really suspect that it cannot be done in a day. That's how things used to be, okay? Well, the reason why that is the case is because the behavior of the program, in other words, how it does things, is wired, is hardwired by the switches, by the actual physical wires, and so on and so forth. Okay? There is memory in these machines, but the memory is only used for data. Just kind of imagine with a C and C++ program, the data is actually still in RAM, but your program is not. Your program is physically wired. Okay, that's how these computers used to be. Okay, the behavior, the actual algorithms are hardwired. So the next picture is the ENIAC, and it says the ENIAC can be programmed to perform complex sequences of instructions. It even has the concept of loops, branches, subroutines, and whatnot, which is actually a big change from the Colossus. The task of taking a problem and mapping it into the machine was complex and usually took weeks. Okay, so I corrected myself, okay, not days, weeks, okay? So it takes weeks to reprogram this thing so that it can, work on a new problem. You can solve different types of problems, okay? And then it says right here, so the program has to be figured out on on paper, okay, not a piece, probably a pile of paper in this case. And the process of getting the program into the ENIAC by manipulating its switches and cables can take days. So I guess the weeks included the paperwork, okay, to figure out, okay, how should I wire this thing up, what switches to turn to which side, and then even after the specification is done on paper, the people who are doing all the mechanical stuff to actually rewire the thing and flip the switches, that will still take days. So we are talking about computers that are programmable in a way because you can change the behavior, but not in a very convenient fashion. Okay, so that's kind of that's how things used to be. Okay, so by today's standard, if you think about how complex your apps are getting these days, think about the length of the programs, of the Linux operating system. If everything is still done by wiring and turning switches and stuff like that, it would take years before you can upgrade from the one version of Android to the next. The ice cream would have melted.
That's good.
So we don't have problems like this And computer science, not computer science so much, but computer engineering and also the technology can advance so quickly, all thanks to one particular person who changed this picture into something that we are currently using, okay? And guess what is the name of that person? Von Neumann, yes, okay? So I always thought it was called von Neumann, okay? And I was corrected that it is supposed to be von Neumann. Huh? Von Neumann? Von Neumann. Okay, thank you. Because is it Deutsch? Is it German? Sorry?
Hungarian.
Ah, okay. So here's the picture of the guy who is responsible, and now, excuse my mispronunciation because it takes me a lot of time to rewire my own brain to say something correctly. So von Neumann, okay, was the first person to come up with an idea which was considered radical at the time. Okay, do not use RAM just to store the data. Use it to store the program as well. And he was the first person who came up with that idea. Because before that, the program, the behavior of the program or your computer is only done configured by hardwiring and stuff. Okay, and he's the first person who said, well, is it possible to change that so that the program, in other words, the code or the configuration that affects how things is done is also stored in memory, just like the data that is being processed. And he's the first one who proposed that. And that turned out to be a very, very important concept in computer science, because without this idea, we'll still be doing wiring, okay? And it would just be possible on cell phones because things are so small, right? I mean, what are the switches, in your cell phone? How do you rewire things in your cell phone? You can't, okay? There's so many connections. So he's the first person who came up with that idea. And the basic idea is this, okay? The concept of storing instructions in memory means that instructions are represented by bits, okay? In other words, instructions are no longer represented by wires, okay? I go from this thing, this circuitry, to this circuitry here to mean that after doing this, you need to do this. It's now just a part of the memory. You have instructions to execute, and instructions are stored in memory, just like the data. Are we still doing okay so far with his contribution to computer science and why it is significant? Okay, very good. So since most of the classes here, I'm going to pass the row sheet because this is one of the very few days that I actually remember. All right. So it is important to realize the importance of John von Neumann's idea. Without his idea, there won't be any downloading of programs. Because when you're downloading programs, the program is not just downloaded, it is also being installed automatically onto your devices. Now, just for historical reasons, I just want to show you guys, the advance of memory. Okay, so even with von Neumann's idea, the part of your computer that stores the program has changed a lot over the years. Okay, it started off with ROM. Okay, you don't have to write this down because I'm not so interested. Read-only memory. Okay. And most people know what ROM is, right? Because you have encountered ROMs in your BIOS, okay, on your computer. And most cell phones actually has a rescue or a very low-level part that allows the cell phone to be reprogrammed. Even if you break it, you can still put it into a certain mode so that you can reload the most basic stuff into your phone and gradually rebuild the whole thing so it's not useless anymore. So that stuff is in ROM. It's read-only memory that cannot be erased, okay? The original ROMs were can be hardwired, okay, for one thing, okay, read-only memory can be hardwired. It's just the circuit built that way and it cannot be changed. But people quickly found out that, hey, sometimes we need to change stuff over time, so it's not convenient if you spend a lot of money to make one chip that cannot be changed. So after a while, people came up with the idea of OTP ROM, one-time programmable ROM. So these things are ROMs. They come out of the factory blank, okay, with no programming whatsoever in it. So what you do is when you think, okay, I think this is going to be the BIOS of this particular computer, then what you do is you program it, okay? But you can only program it once, exactly once, okay? And that's why it's called OTP, for one-time programmable, okay? And the programming is done by breaking fuses, of certain parts of the ROM, okay? So if you break a certain fuse, it will change the state from a 0 to a 1. But it is not undoable, because once you break a fuse, it cannot reconnect again. And that's why it is one-time programmable. And the machines to do the OTP are very specialized, because it takes like a higher voltage to do the programming part. So that's the good old days, and obviously it's not very cost effective, because one chip can only be used once. Okay, when you say, okay, this is not the program that I want to be on this chip anymore, then you have to toss the chip away, get a different one, reprogram it, and put it onto your whatever circuit board that needs that chip. Okay. So the next one is called, so this is also called just PROM, for programmable ROM, but it implies it is one-time programmable. So at some point, people came up with the idea of EEPROM, okay? E stands for erasable. So this is erasable, programmable, read-only memory. So these are the ones where you see a little optical window in the chip, usually in the form of a circle that is transparent, okay? So the way it works is, you can use UV, ultraviolet light, to erase an existing program, and then reprogram it, and then if you don't like the program, you can erase and program again. But the downside is it takes 15 minutes of exposure to high intensity UV to erase the program. So it still takes time to do it, but it is a lot better compared to just PROM, because now you can reuse chips. And when I started to get into industry, some in 1990, they were using EEPROMs a lot on single board computers. And I was the person who was responsible for the firmware part of these single board computers. The firmware part is kind of like the ROM part. This is the part that runs before everything else. When you power up, it's the ROM, the firmware that gets controlled first, okay? So it's a little bit hard to debug those things, because where's GDB? No. Where's Linux? Doesn't know Linux, okay? Where are all the other tools that can help you debug your program? You don't get any, because when you wake up as the processor, you don't even know where RAM is. So you have to do some certain exercises, on the memory bus, just to find out, okay, I think RAM is located here, but how much RAM do I have? Is it 4K, 16K, or 32K kilobytes, right? Yeah, because people are not used to those units anymore. And so you have to do all these things with no assumption whatsoever that you already have RAM available. So you cannot use variables. You have to do everything without a variable for a while until you get to RAM. So I have to write the firmware, and the firmware exists only in EEPROMs. So if I make a mistake, it doesn't work, I have to remove the chip from the board, okay, but they're in sockets, which makes it a lot easier, okay? So you just use a socket, you get it out of the board, you get the next one in, because it doesn't make any sense to only use one single EEPROM chip. So I usually have like 10 of these things, so I can basically just use up all 10, then I erase 10 all at the same time, then I have 10 available to do the debugging. But there's no tool to do the debugging other than a single LED in most cases. Did I get there? Turn on the LED. Yes, I got there. Good. And then you move the LED, code a little bit downstream and go like, okay, did I even get there? Okay, that's how I debug programs. Okay, and it's not instantaneous like, oh, I changed the program, click a button, and the whole thing will run by itself. No, you have to remove the chip, remember? Okay, then you go to a different machine, you reprogram the EEPROM chip, take it back to the machine that you are running it on, put it into the socket, power up, and only to see that the LED did not turn on. Then you get back into the coding part, fix the program, and then repeat the whole cycle. And that was only about, what, 25, 26 years ago. Okay? Now, if you think about 26 years, most people say, well, that's older than I am, right? So 26 years sounds like a long time. But if you look at how cars have changed in 26 years, not really that much. Look at internal combustion engine, not really that much. But when you look at computer stuff, wow, that's a huge, complete change. So after EEPROM is EEPROM, double EEPROM, that's how it's called. So EEPROM part is still the same. It is erasable, programmable, read-only memory. The extra E stands for electrically. So now it is not based on UV, it is electrically erasable, programmable, read-only memory, okay? So EEPROM has a very big significance because it is electrically erasable. You don't need to remove it from you don't need to expose it to UV for one thing, but some of these can be done in place without having to remove the chip, okay? Which leads to the next one, which is flash memory. So these two are closely related, but one is usually associated with a much smaller capacity, and the other one has a much larger capacity. So and also one big difference is the EEPROM requires a different voltage for erasing the chip, whereas flash memory only has one single supply voltage, which is a big, huge help because that was making a flash memory so popular, because on the circuit board that makes use of flash memory, you can do the reprogramming part without all the extra voltages that you also need in EEPROM. So that's kind of a brief history of read-only memory, which we use for storing the startup code. Yep.
Flash memory can only be re-encoded every so many times. Same for EEPROM and EEPROM?
Yes, they have a limited number of cycles. So OTP, that's one time, right? EEPROMs, they do degrade over time, and after a while you cannot reprogram anymore. The typical problem with the EEPROM is not that you cannot reprogram it, but you cannot erase it. So it stops to be erasable. EEPROMs and flash memory, they all have a certain number of cycles. Now, back in the days, when I first used flash memory, you can only have about 10,000 write cycles to each section, and that's it. Okay. I'm not sure about the standard now. Does anyone know? How many times can you rewrite a section of flash memory these days before it quote unquote runs out? I'm guessing it's probably in the 100,000 cycles.
It depends on the kind. Like the stuff in a solid state drive, that's 100,000. But like the stuff built into like a microcontroller, that can be like 1,000 even.
Oh, it's less than 10,000?
Yeah, it can be like a few. It can only be like 4,000.
Okay. Well, thank you. That's good information there. Which also means when you get a solid state drive, the sectors can only be overwritten a certain number of times. Now, when you look at that and you look at certain design of file systems like FAT32, FAT stands for File Allocation Table. So every single time you want to delete a file, it touches the FAT, which is a particular sector in the file system. So you can probably imagine it doesn't take very long to use up all 100,000 cycles because of the fact the file allocation table needs to be overwritten very, very at a high frequency. So the earlier solid state drives would basically burn out because of the inefficiency or the design of the file system. It wasn't designed for that type of device. But when you buy a solid state drive these days from any place, the solid state drive that claims to have 128 gigabytes actually has more capacity than that. It's just that internally there's a processor that will manage all of these things. It will keep track of how many times an internal sector has been overwritten, and it will do the load balancing thing. And it will go like, okay, this sector has been used a lot more than the other ones. Let's stop using this one for a while and bring the cycle up on the other ones first. So there's already, there's an actual processor inside your solid state drive that's doing all this load balancing. So what you consider as sector 0 of the entire drive does not even map to the first sector of the actual internal memory. It's all done. The remapping is done on the fly as you access a drive by the processor that is built in to the drive itself. In other words, your solid state drive itself is a computer.
It has a mind of its own.
Yes.
What about MSATA? MSATA solid drives?
Same thing. Anything that is a solid state drive needs load balancing. Because otherwise, if you overwrite a particular sector a lot more, then your drive will fail a lot faster than it claims to be able to last. Yep.
Does this also apply to RAM in terms of how many cycles you can?
RAM does not typically has a cycle limit, because RAM does not use the same mechanism to store information. So with RAM, the only lifespan that affects RAM also affects every single semiconductor. It has to do with the unintentional migration of the quote-unquote impurity of semiconductor. Because semiconductor, as the name implies, means it is sort of a conductor, right? But when you look at silicon, pure silicon, do you think pure silicon is a conductor? No, it's not, because there are no free electrons to flow around, so it is not a conductor, it's an insulator, right? So the only reason why semiconductor is semi-conducting is because of the introduction of impurities, quote-unquote impurities, which is usually germanium on one side, and I cannot remember the other side. But one would give it extra electrons that can flow freely, and the other one will give it what we call holes, which is the lack of electron that can also move freely, and that's why it can do the semiconduction thing. But the material that is kind of integrated into semiconductor can migrate, as time goes on. So that's why, chips can degrade over time, because, these impurity particles can actually migrate. They're not locked in place. So when they migrate, then your semiconductor, whatever device, will start to lose its capability of doing what it is supposed to do. All right. So that's von Neumann's idea. For those of you who are interested, you can also just go ahead and search for this name and look up Wikipedia, because it is a very, well, personally, I think it's a very interesting read to read about the history of this guy, because he is referred to as the genius by geniuses, or genii, I guess. What is the plural of genius? Geniuses? Okay, my INTP plus ADD nature makes me do this. Okay, so we say nope, not ADD. Okay, see, that's my ADD kicking in right away. Okay, I'm looking up. Oh, yes, thank you. Okay, yes, you use genii instead of geniuses when you don't want to be easily understood. Fine.
So geniuses.
Okay, stick with geniuses. Okay, well, okay. Okay, but this is from Stack Exchange. I probably should refer to Webster for the definition. Okay. Does it say about the plural?
No. Full definition. Genii.
Genii or genii.
Or geniuses.
Gene.
Left.
Genie. So it's just genie. Of course, that doesn't work because I did not turn on the volume. Okay, so genie. Okay, but anyway, he was referred to by his peers. Now, guess who his peers are? Now, this guy works in so many different fields. Okay, think about Turing. Okay, who's Turing? The father of computer science, right? He's a mathematician. He's basically the first computer scientist. But basically, all computer scientists are mathematicians, because computer science really is a branch of mathematics. So Turing is really good at certain things, but he is only pretty much good at one area. Think of Einstein. What is Einstein good at?
Physics.
Physics, okay? Particularly relativity. The guy could not accept quantum physics. I think in his own words, God does not play dice.
To which Bohr responded,
To which Bohr responded, "Don't tell God what to do."
Yep, exactly. That's good. Yep. So anyway, Einstein is good at math and physics, but that's about his major contributions are. Okay. Well, he figured out E equals mc squared, which also led to the nuclear bombs. But he was not really a pragmatic person to work on the bombs. Von Neumann is. Okay. So he's good at mathematics. He's good at computer science, engineering, statistics, a whole bunch of stuff. Okay. So if you're I think it's interesting because I think reading his history is inspiring. I just have to find out where it is. Okay, there we go. Okay, so just kind of look up. Okay, these are the things he's good at. Okay, when I say good at, he means it's really good at. So it includes mathematics, and within mathematics, it includes the foundations of math, functional analysis, blah, 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 keeps going on and on. Okay? He's also good at physics, but when it comes to physics, he's also good at multiple branches. Okay? Quantum mechanics, hydrodynamics, quantum statistical mechanics. He's good at economics. He's good at computing. He's good at statistics. And his contribution in computer science includes the architecture that we are talking about, but also a whole bunch of other stuff that we do not hear about most of the time. Self-replicating machines.
Wow.
He thought of that stuff in the 50s, way before Stargate, SG-1. The replicators, the bugs, yeah. or even Star Trek, right? I mean, this is way before Star Trek. So the guy came up with all of these ideas, way ahead of his time. He's also the pioneer of the application of operator theory to quantum mechanics. Now, quantum mechanics all by itself is very interesting because I was just watching a whole bunch of video on Schrodinger's cat last night. Okay, because that kind of stuff just kind of intrigues me, and I'd like to kind of gnaw on that sort of stuff. But he has a lot of contributions. He is referred to by his peers, which are the physicists, okay, well-known physicists, well-known mathematicians, as the genius of the field, when he is good at different things at the same time. So why don't we hear of him more often?
He didn't make a lot of money.
Because he's dead when he was only in his 50s. He died in his 50s from cancer, and most people believe that his cancer was probably the result of his participation in the hydrogen bomb experiments. Yeah. Yeah, but he was a hands-on guy. I mean, he doesn't just say E equals mc squared, the rest of you go figure out how to make use of that. He actually go help build stuff, okay? The guy also shared the same hallway in Princeton University. Okay, who else is at Princeton University as a professor? Well-known, physicist.
John Nash? Wait, actually,
No. John Nash does not overlap with this guy. Einstein. So Einstein was actually in the same hallway at Princeton when this guy was teaching at Princeton. Now Einstein, prefers to have a quiet environment because he's an INTP personality. So he likes to be by himself without distraction so that he can think about stuff and work on problems. This guy likes to play loud polka music when he's working. So you can kind of imagine how those two interact.
You can actually listen to more than one record at a time.
Sorry?
You can actually listen to more than one record at a time with different albums playing at the same time.
Yeah, and Einstein prefers to have nothing, right? It's like, okay. And noise canceling technology, unfortunately, was not available at the time. So you can kind of imagine conversations on the hallway. It's like, shut up! And then this guy just go like, okay, crank it up a little bit.
Probably got along great with Feynman.
Well, Einstein has a big ego as well, which is probably, which means it probably does not work. Okay, so what we're going to do now is to take a look at how memory is organized in a computer, because that is the crucial part of the von Neumann architecture, is Okay, but how do we get instructions into memory, and how do we execute instructions? Okay, so we're gonna get into that part here. And the first thing that is really helpful in this process is to start up logic sim. So I'm gonna start a logic sim, and I can remember where I put mine. Yep, there we go. All right, so logic sim is not really just a tool. Okay, if you go to the help here and go to, not tutorial in this case, but go to library reference, you can look up memory library, and it has all kinds of stuff that we haven't really talked about. But today, what I'm more interested in is just ROM. Okay, so we'll just pick ROM today. This is how ROM looks like in logic sim, and it has A on the left-hand side. Let me just point out what I'm talking about here. So this A is called the address bus. This D is called the data bus, or data access, and SEL, S-E-L, stands for select. Okay. So what we'll do today is really just to go through a few exercises making use of the ROM chip and see what we can do with it. Okay, is that okay so far? Okay. Because this is one of the centerpieces of the modern day architecture. It is not RAM because we cannot write to this type of memory, but it still illustrates a lot of key ideas of how to make use of memory. Okay, so we'll start with this one. And I'll just pick out a ROM and put it here, and we'll just magnify this a little bit so that it's easier to see the entire thing. There we go. And center. Oh, it doesn't like to be centered. Okay, there we go. So this is a ROM chip. If you hover your pointer over these ports, it will explain what it is. It says it's the address bus, location accessed in memory. In other words, this particular interface tells the ROM chip which location do you want to access, okay? Because somebody else wants to access the memory, and this is how you tell the ROM chip, hey, I want to access location 56, okay? Once location 56 is addressed, okay, it needs a way to tell whoever is inquiring and say, oh, location 56 has a content of, let's say, 7D, okay? And this is the interface to do that. It's the data port. It specifies the value loaded from memory, okay, loaded from this chip. The extra one, the third interface, which is select, is just basically kind of like an on-off, because we would like chips to be hooked up in a bus configuration, which means we'll have parallel chips connected to the memory bus. They're all connected in the same way. So the only way you can say, oh, I want your location 5 and not your location 5 is the selection pin. The selection pin is the only one thing that is specific to each memory chip, as opposed to shared by all different chips. Okay. All right. So what we'll do is I'm going to replicate this so that we have two of these. Okay. And we can change the address bus by by changing that. You are basically saying, okay, how many locations do we have in this particular memory chip? The default is 8. Okay, in other words, we have 8 bits to specify which location we want to access. So how many locations are we talking about? Given the we have 8 bits to specify a location on the chip.
8 locations.
256.
256 is correct, okay, because 2 to the power of 8 is 256. So the number, as a binary number, goes from 0, 0, 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1, 1, 1, 1, okay? So with 2 chips like that, I should be able to access 512 bytes, because one chip has 256, so both, when I combine the 2 chips, I should have 512 bytes of locations. So what I'll do is I'm going to wire up these things. So remember, the address bus is shared. The data bus is shared as well. The only thing that is not shared is the selection. Okay, so the selection is not shared. I will bring this up to here, and I'll bring this one up to a different pin. Undo. Okay, all right, and we'll also. The next thing I'll do is, okay, I cannot really see what is going on, with just the wires. So what I'll do is to use input pins and output pins, just like in your homework assignment, so that I can visualize what is the data bus outputting, and I can also control what the address bus is specifying. Okay, so to do that, it's just the same way as we usually do it. We have an input pin to specify something that is an input, okay? And the input pin in this case goes to the address bus, because the address bus is what is telling these two chips which location to access. Now, when you see an orange wire, you can read the bottom of the screen, which many of you cannot because you're in the back of the classroom. It says incompatible widths. And that's because the width of the A interface is configured to be 8 bits at this point. But the input pin is configured to only have 1 data bit. So it's time to change this to match the width of the address pin. So now it has the correct width to do that. And let me just kind of move the whole thing. It looks ugly, but I guess it works. There we go. So that's how you can change the width of a quote-unquote wire to also handle multiple bits. Is that okay? Sort of? Because otherwise, it's really cumbersome if you just expose individual bits of the address bus. Then I have 8 wires to connect all over the place, which is no fun. So it's much more helpful when you just combine all 8 wires and say functionally they serve one purpose, and therefore we bundle all of those individual wires into one big fat wire. Yep.
So is the A going to be the location on the module where you write to?
The port A is what you use to tell the memory chip which location you want to access. And you can also tell right away that both chips are now selecting location 0 because that is what the input pin is specifying. Okay, so let me just kind of play around with the input pin a little bit so you can see how different locations are selected. Okay. So we can change this to a 101, which is location 5, right? So okay, here we go. 101. This is location 5. You can count 0, 1, 2, 3, 4, 5. So by manipulating the address bus, okay, the state of the address lines, you can now specify which location you want to access on each chip. Okay, so that is all good, except what is the actual output from the data port of both of these chips? And what I'll also do is something like this. Okay, I can change. You can also change the memory content of ROM in the simulator just by writing over it. Okay, click the location and then just overwrite it. So for this one, I want it to be 78 in hexadecimal, and then for this one, I want it to be, let's say, 13 in hexadecimal. I just want them to be different. That's all. Okay, and you can see that this wire is going red. Okay, when a wire goes red, that means you have a conflicting signal, otherwise known as a bus fight. Okay, a bus fight. I mean that's a real term, bus fight. A bus is basically the same thing as a multi-signal wire that we have here. Okay, that's called a bus. In industry terms, it's called a bus. So we have an address bus to specify which location we want to access, and then we have a data bus so that we can see what is the actual content at that location. But since the two locations on the locations on each chip corresponding to location 101 in binary are different. So one guy wants to output 0111 10000, which is the binary representation of 78 in hexadecimal. The other one wants to output 0001 0011, which is the binary representation of 13 in hexadecimal. They are not the same. Okay, so for these individual wires in the bus, okay, one chip wants to drive it high, the other chip wants to drive it low. And therefore, we have a problem, because now they're trying to wrestle with each other, to see, okay, I'm stronger than you, and so I'm going to force the line low, even though you want to drive it high. And usually, because of the use of N-channel MOSFETs, for the most part on our chips, the circuit that tries to drive it low would win. The circuit that drives it high is actually, doesn't drive as much as the circuit that drives it low. Okay, so but nonetheless, we have a bus fight. So what actually happens in reality in physics when we have a bus fight? Okay, this is a question for those of you who have taken a physics class in electricity. So you have basically one chip trying to drive it high. Okay, so let's say 1.8 volts is high. The other chip wants to drive it low, which is 0 volts. Okay, so this is coming from one chip, this is coming from another chip, and there's a wire connecting these two. What's going to happen? Well, the wire actually has a little bit of resistance. Okay, everything has resistance. So there's actually an inherent resistor between these two. So what is going to happen with this resistor? Well, depending on the value of the resistor, right? So let's say this is R, okay? So the amount of current that is flowing through here is what? I is voltage differential divided by R. This R is typically in the range of, I would say, probably 1 ohm or something like that, okay? So let's say this is 1 ohm. So you're dividing 1.8 volts by 1 ohm, which is 1.8 amps. And to us, 1.8 amp means, so what? Big deal, right? Because a light bulb, the good old-fashioned light bulb, a 100-watt light bulb will consume about 1 amp at 100 volts, right? So 1.8 amps is not much, especially if you work with heavy machinery or hair dryers. Okay, hair dryers are notorious of consuming a lot of ampere, in the order of 15 amps or so. So 1.8 amp doesn't seem like much. Well, except how big are these transistors? They're tiny. Okay, to be exact. Okay, how many people have been keeping up with the sizes of transistors, like Intel stuff? Is it 20 something now, or is it lower than 20 now?
It's like 14.
Huh? 14 nanometers, right? 14 nanometers, and you're trying to dissipate how much power at that with that area. Well, what is power? Power is voltage times current times voltage, IV, right? So in this case, you have 1.8 amps and 1.8 volts. So it's 1.8 squared. I'll just call it 2 by 2, which is 4. Okay. So you have 4 watts of power to dissipate in a tiny little chip or tiny little transistor that's only 20-ish nanometer square, 20 by 20 nanometers. That's not a whole lot of surface area, is it? People talk about, if you just cut one hair, okay, the cross section of your hair is big enough for a large number of transistors already. That is how small each transistor is. And yet you want to dissipate 4 watts. Psst, gone. So when you have a bus fight with any type of semiconductor these days, it simply means the device itself will kill itself. Now, it's not even going with a bang. You would think, oh, it's worth it if I can see a big old explosion. Nope, that's not what you're going to see. It will just stop working. You won't see any explosion. There won't be any fire of any kind. It just stops working. Because you just burn out individual transistors. And usually without any visible sign whatsoever, and your chip just dies. Yep.
In my electronics class, we called it letting the smoke out.
Well, I make it more mythical.
Yeah.
I call it letting the genies out.
Yeah.
That's why your chip doesn't work anymore, because the genies have left the chip. Okay, so let's go ahead and see what is on this bus. How is it represented as an output pin? So we'll go pick out an output pin. Okay, we'll stash it here. We'll probably have to reposition it a little bit later on, and hook it up to the bus. It's kind of like a probe. For those of you who have taken classes in electronics, you know what a voltmeter is. Okay, so this is kind of like a super fancy voltmeter that can measure the voltage on multiple wires at the same time. Once again, we see the orange wire because the widths are not agreeing, because an output pin by default has a width of 1 bit, and yet the data pin here has a width of 8 bits. So it's easy to fix. Just change the pin to all this stuff here. So when you see the E, it is not in hexadecimal E. It is quote unquote error. In other words, the simulator says, I don't know what this wire is. Okay. What about the zeros and the ones? That means the 2 chips agree on those individual bits. So you don't have to fight over those particular bits. The E's are the ones where they do not agree and go like, I think this, okay, let's just use this example, okay? In the 7 of the 7, 8, it is in hexadecimal, and 7 is 0, 1, 1, 1 in binary, which is corresponding to this one over here in hexadecimal, and in binary it is 0, 0, 0, 1. So they only agree on the least significant one, which is why you have a 1 at the output pin. But the other 2 bits are different. The top chip wants to output a 1, drive the line high, and then the bottom chip wants to drive it low because it has a 0. And that's why you see the 2 E's after the 0 and before the 1, because they cannot agree. And this is a bus fight. And as I said, if a bus fight persists over time, the chip will die. Because usually it's the one that tries to drive it high that will die first, because most chips can drive high with less current than they can drive low. Is that okay so far? All right. Okay. So how do we resolve this problem? Because you're probably not trying to read both locations at the same time. You probably just want to read one of those. So what we need is a way to specify, hey, chip number 1, I want you to pay attention. Chip number 2, shut up. So that's what we need. So we'll hook up both at the same time first, okay? And you can see now the output pin specify XXXX, which basically means no one is driving the wires, because we are feeding a 0 in both chips to the selection pin. In other words, you're telling both chips, don't pay attention, not talking to you, right? And you can even see that none of the location is selected, because if the chip is not selected, it does not even pay attention to the address bus. Are we doing okay so far with this picture? What each port is responsible for? Okay? All right, so let's just say that we want to access location 5, and the first chip has location 0 to location 255. The second chip has location 256 to 511. Okay? Because that's how you can get a larger memory space when each chip only has 256 locations. Is that making any sense? Sort of? Okay? I'll use an analogy later on. Okay? So if I want just location 5, that means I want to talk to the first chip, the top one, and then just say, hey, top chip, pay attention now. I want you to give me your location 5, and now we don't have a problem, because now we have 0, 1, 1, 1, which is 7, 1, 0, 0, 0, which is 8. Okay? Now, what if I want location, let's see, 256 plus 5, so that will make it 261, okay? So in the logical space, okay, I want to access location 261, which in this design here corresponds to location 5 of the second chip, because location 0 of the second chip, of the bottom chip, is actually logically location 256 to continue from the previous chip. So if I want to do that, then I just say, hey, the bottom chip, go pay attention now. I want your location 5. Tell me what it is. It is 13 in hexadecimal, which turns into 0001, 0011 in binary. So that's how memory works, okay? Now this is greatly simplified compared to what you have in a computer, but in terms of principle, it is really the same. You have an address bus to tell the chips which location. You have a data bus so that the chip can tell you what is the content at the location. And you have a selection pin to say, okay, chip number blah, okay, I want you to pay attention and everybody else shut up. Is that okay so far? Okay. So just to give you a quick analogy of how to combine multiple chips so that we have a larger logical memory space, okay? So we'll just say that these 3 people on the front row here, each person has a 100-page binder, okay? So combined, they have 300 pages. Does it make sense? So, and I'm the person who wants to access those 300 pages. So if I want to address page 250, then I'll go like, okay, you have page 0 to 99, you have page 100 to 199, and you have page 200 to 299. So you are the one with the page that I want. logically. But to you, to the memory chip, it is not location 250, it is location 50 on his book. Okay, but from my perspective, because I am the one who is seeing all three chips, so from my perspective, it is location 250. So what I do is I'm going to scream out page 50 to all three chips. Okay, but since the first two chips are not paying attention because I'm not, addressing them, they will just ignore my screaming, go like whatever. Okay, they're not going to do anything. Except the third chip, because I'm just going like, hey, I want your attention, page 50, please. So he's going to reply and say, oh, page 50 has this content. But since the other chips are not talking, I can hear the one that actually has the content that I want without any problems. Now, if the circuitry has any problem and multiple chips are selected at the same time, then they will try to talk to me at the same time. Then I won't be able to figure out what is the actual content on the page that I want. And then they will fight with each other too, because they will disagree and say, but it's 5.6 in my book. No, it's 1.7 on my book. And they will start to have a fight on the bus. Yep.
Does the structure of the ROMs matter?
After school, all of those guys.
What do you mean by structure? How it is
How they're
arranged?
arranged, so because the current reaches the top one first. So
No, the ordering does not matter because this is really just logically displaying that we have the same wires going into both chips. So I can space them out, put them upside down, and whatnot. It would not really change the logical way of the logical connection of these pins. Will do not change by physically moving them around. Yep.
How does it know to automatically select location 5?
Well, that's a whole different thing. So the mechanism that is responsible to specify the address bus, the mechanism that is responsible to say, okay, which chip should pay attention, and the mechanism of, okay, who's really paying attention to the output of the chips, that's all kind of secondary in this discussion. Okay, so we are not going to touch on that until we get to the mechanism of interpreting instructions, to decode stuff and whatnot. Yep.
you drew that analogy earlier with the 100, 200, 300 pages. What here determines which is the hundreds, which is the 200?
Well, that all depends on how you label the chips. Okay, so if I want this to be the first chip, quote unquote first chip, and this one to be the second chip, then I'm gonna, it has to do with how you label the pins and also what drive these pins. Okay, but I'm not there yet. So at this point, there's no inherent ordering to these two chips. I'm just labeling one as, okay, your chip 1 and your chip 2. Because it's the same thing with these three people in the front row. I can read it from left to right. I can assign who has the first book, who has the second, and who has the third book in any order that I want. So that mechanism has not been specified yet. Mm-hmm.
What happens when you have a chip that has a different capacity?
Then you have, well, okay, you can mix chips with different capacity, but whatever is driving the mechanism has to understand that part, so that it can calculate which chip has the select pin activated. So you can mix different capacity. It's just that you have to be careful, when you calculate, which chip should have the select pin activated or asserted to be, using the terminology of EE. Any questions about this picture? No questions about this picture? Yep.
So say you wanted to access, because you said each chip has got 256 locations
Okay.
in it. So how would you pick, I don't know, location 40 on one chip? Say you only had just the one chip. How does it know where that is? I didn't count those,
Okay.
but it's not, there's not 240.
So not displayed in this circuit would be a mechanism that will basically dictate which chip is responsible for which memory range or what location range. So in this case, if I designate this is the first chip, then the first chip is responsible for location 0. Okay, this is all in decimal because we haven't really talked about hexadecimal yet. So this is from 0 to 255, and then this one is going to pick up from 256 to 511. So given this particular ordering, then this pin here should be labeled. Now this is just an industry standard. It is usually called CS0 for chip select 0, and then the other one is going to be CS1 for chip select 1. It is the selection pin of chip 1 or the selection of chip 0. Is that answering your question? But why I picked the top one to be chip 0, that's just random assignment at this point.
With that exactly, but I don't know if my question can be answered right. Like number 78 tail in there. What location is that occupied?
It's 78 in hexadecimal. That's according to the way I assign the addresses. The location that has a content of 78 is 05. It's 05 because everything on the top chip, according to this assignment, would be location 0 to 255. But on the chip itself, the first row would start with location 0. The second row starts with location 4. So this is location 4. This is location 5. Is that?
So there's really like more zeros. We should only representing a few of them there.
Say again?
There's really like more like
Columns and rows.
yeah, columns and rows. You're just only representing a few of them there.
Instead of printing all 255
Yeah.
individuals.
Yes. So
Okay.
if you want to see all
Okay.
255, you can
That
double
makes a
click
lot more
it,
sense now.
or right click and then edit content. There we go. So now you have a full map of all the locations.
Now it's more sense.
And you can save it too. You can also, after you save, you can load the content back, which is really handy for homework assignments.
I'm just double checking that the numbers on the left hand side of that were in hexadecimal, the line numbers.
Yes, those are in hexadecimal. All right, so I guess it is inevitable to talk about hexadecimal because it is used very often in software like this. So let's go ahead and I'm just switching gear a little bit to talk about hexadecimal, which should be a fairly quick topic. Okay, actually I want to change to a spreadsheet because I want a table type of representation. So let's go ahead and switch to a spreadsheet. You guys don't want to see this anymore. Okay, so let's talk about hexadecimal versus binary. Okay, so I want someone to give me the binary representation of the first 16 numbers from 0 to 15 in decimal. What is the binary representation of all of those values? Okay, so first of all, we'll do it in base 10 first. Okay. So to do it in base 10, okay, it doesn't do. Oh, that's an O. Okay. All right, there we go. That works. Okay, so 15 numbers. Okay, so now I want the binary representation, but I want all 4 digits. Okay, because the 15 requires 4 digits to represent it. So what is 0? How is 0, the value 0, represented using 4 bits?
0, 0, 0, 0.
Yep. Okay. Sounds really boring. Okay, 0, 0. Oops. Ah, I cannot type. There we go. There we go. All right. So 4 zeros represents 0. Okay. What about 1?
0, 0, 0, 1.
Yep. Okay. What about 2?
0, 0, 1, 0.
0, 0, 1, 0. Because you add 1 to 1, you get 0 with a carry. But that carry in this case has a place to go, which is the 1 of bit 1.
In
0,
spreadsheet,
0.
we have to do the apostrophe.
Huh?
In spreadsheet, we have to do the apostrophe for
0.
Right, because otherwise it will consider 0001 or 0010 as a 10.
Oh, okay.
Yeah, because it doesn't understand binary numbers. Yep. Now there's a way to do base conversion in the spreadsheet, but I don't want to do that because I want to kind of go through the exercise with you guys. Okay, the next one is 0, 1, 0, 0. 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. Go.
1, 0, 1, 1, 1, 1.
And the last one is 1, 1, 1, 1. Okay. So, not too bad. So now we want to say, okay, this is all good, but this is one drawback of binary numbers, okay? Remember how I like binary numbers? Because when you deal with addition, there are only 4 rules to remember. Of the 4 rules, only one is kind of special. The other 3 are really obvious. Same thing with subtraction, okay? So with binary numbers, it's really easy to teach addition and subtraction to someone who has not been exposed or poisoned by base 10 numbers. You are all poisoned. That's why you think, oh man, binary addition and binary subtraction is so hard. Well, that's because you have been doing the wrong way for what, 20 years or so?
All math is wrong.
But there's one problem with binary numbers. As fantastic as it is, okay, it has one problem. It takes way too many digits. Exactly, it takes so many digits to represent something that is meaningful. Okay, what is the deficit of the United States?
Trillion.
0.0000000.
It's a trillion. Okay, so let's say how many trillions?
Dude, it's like near 20
trillion.
Now I need to find out.
Like near 20.
See, you can see how at the end of a semester, I usually do not end up teaching everything that I need to teach.
Slowly burning, bruh.
U.S.
hours.
deficit.
Better what?
Okay, so it's 1 point something trillion. Okay.
1.4 trillion.
Oh, that's only as of
Look at the.
That's what it says in
It's
15.
Look at the debt
currently,
clock.
as of
Debt
April,
clock, okay.
500 billion.
There you go.
real time.
It's like
Ooh, look at that.
20 trillion almost.
So 20 trillion. Okay, so let's think about 20 trillion and how many binary digits we'll need to represent 20 trillion. Okay, so you guys might think, okay, I need a calculator to do that. Well, if you have a calculator, it's pretty easy. Okay, what you do is you take the log, take whatever base of the log you want, you just have to be consistent. So just take the log of 20 trillion, take the log of 2, divide those 2, and you have the number of digits required to represent 20 trillion. Okay, what if you don't have access to a calculator? Well, then you use a rule of thumb. Every 3 digits in base 10 is 1,000. 2 to the power of 10 is 1024, which is close to 1,000, just close enough, right? So you just basically say, okay, we need 10 bits, 20 bits, 30 bits, 40 bits to represent a trillion, okay? And then this number is just, it's more than 16 but less than 32, so you add the other 5 bits to it. So we need what? I lost track again. 45 bits, I think?
42.
42?
That's why you have a logarithm.
Okay. Okay. 10, 20, 30, 40, and then 45. Well, the 1024 is not exactly 1,000, but I did not think it would make that much of a difference. But 40-something bits, I think. Okay, now I need to figure out whether I got the math wrong or not. Since we have a spreadsheet up, it's easy to figure it out, isn't it? So we say the log of 20 trillion, 3, 4, divided by the log of 2.
You forgot
Oops.
0. Yep.
Oh,
Air
okay.
state.
Doesn't look like that. Okay. 1, 2, 3, 4. There we go. 44.
I dropped to 0 back.
Okay.
A lot of them.
Okay, so I was close. Okay, so 45 bits because you have to round up to figure out the number of bits. So 45 bits, which is exactly what I said a little bit earlier. So you need 45 bits to represent the United States deficit. That's a lot of digits, a lot of zeros and ones. Okay, so we say, well, that's not very handy because now, in order to write those numbers, okay, just look at the look at this page here. If this is all represented in binary, instead of using 12, instead of using 14 digits here, we need 45 digits all the way here to represent one single value. That's not handy. So people would say, Z-Tech told you base 2 sucks. Then I would just reply and go like, well, maybe base 2 sucks because it doesn't, it's not compact, right? What about base 16 then? Aha, see, base 16 is really cool. It is just as cool as base 2. Okay, so let's take a look at base 16. Base 16 simply means that one single digit can represent a quantity from 0 all the way up to what we know in base 10 as 15. Okay? So the first 10 is really easy because we just borrow from regular base 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we can borrow all of those from base 10. What about 10 itself?
A.
It's A, lowercase a, B, C, D, E, F. That's hexadecimal, okay? And this table, you just kind of have to memorize. I mean, there's really no quick way around this. But it's only a table of 16 entries, okay? The more you use it, the quicker you will get used to it and remember the actual table. Yep.
What does a capital letter mean? Or
The same. Yeah, it's case insensitive. Yep. All right. So, but this table is really useful because the leftmost column is useless. Okay, column A is really useless because that's really just saying, okay, what is that quantity when we want to use base 10? But remember, we want to ditch base 10 altogether. So what is really useful is these two columns. Okay, you just look at the 4-bit pattern, and you just have to remember which hexadecimal digit it corresponds to. Okay, so the conversion between base 10 and base 2 is kind of tedious. Okay, let me give you an example of the conversion. Okay, and for that I'm going to use my document camera because I have it all set up already. It would be a shame if I don't use it. So let's say we pick a number, let's say 413, and we want to convert it into base 2. Okay, you can just punch it in the calculator and do it that way, but what is the fun of doing it that way, right? So we just say, okay, let's divide it by 2. It is 206 with a remainder of 1. Divided by 2, you have 103 with a remainder of 0. 52 with a remainder of, 51 with a remainder of 1. 25 with a remainder of 1. 12 with a remainder of 1. 6 with a remainder of 0. 3 with a remainder of 0, and then 1 and 1, oops, with a remainder of 1. There we go. We are done. Okay. So how do you read all these numbers?
1 0 0 1 1 1 0 1.
But which one is the least significant bit?
The one on the bottom.
No, the one on the top. The top one.
Top one. That's right. This is our least significant bit. We say it is the least significant bit for with a lowercase b, because the uppercase b stands for bytes, okay? And this is our most significant bit here. So that's how you do a conversion, but it involves division, right? So this number is 1100111101. Okay, there we go. All right. So given that is the binary representation of the value 413. What is the hexadecimal representation of that? Ha! Tag, you're going to spend the next 5 minutes doing this.
No,
okay, let's count. Group them in 4 bits. If you have leftover, pad zeros to the left-hand side. Pad more significant digits. Okay? So now that I have this, I can just look up the table. Okay, the table is partially hidden, but I'm going to show it to you guys so that you guys can work this out with me. 1101. Look up the table, okay? It is a D, right? 1001 is a 9, and 1 is just 1. So 19D is the hexadecimal representation of 0001, 1001, 1101 in binary, which is also what we know in base 10 as 413. See, the base 16 to base 2 conversion is just like that. It's just a table. Group everything in groups of 4 bits and look up the table for each one. It's easy. Is that okay? Why do you think base 16 versus base 2 is so easy, but if I want to do conversion between base 10 and base 2, it's so hard? What makes 16 different from 10 when it comes to the base of numbers?
16 is a multiply factor of 2.
It's a power of 2. Exactly, and 10 is not. So when you're converting between bases where one is the power of the other one, you're just combining digits and look up a table and you're done. Okay? So if we were to use base 3 and base 9, that conversion would be a cinch. Because every 2 base 3 number combines to one base 9 digit. So it's just every 2, look up, every 2, look up, every 2, look up. With base 2 versus base 16, because 16 is 2 to the power of 4, we have groups of 4 bits versus one single digit in hexadecimal. Okay? So some people are going to say, okay, but what about base 8? What makes 16 better than 8? Because in base 8, we just need 0 to 7. We don't need to borrow the letters from the alphabet. The problem with base 8 is, how many bits do we have per byte? 8. Okay, there are 8 bits to 1 byte. When you divide 8 by 3, what do you get?
8/3.
Yeah, 2 and, no, 2 and something, right? You divide 8 by 3, you have 2 and a remainder of 2. So that means we're not quite using 3 octal digits, octal means base 8, to represent 1 byte. What about 8 divided by 4? Exactly 2. So we need exactly 2 hexadecimal digits per byte. When you want to represent something that has multiple bytes, it just keeps going, okay? Because the boundary of bytes falls into boundaries of every 2 hexadecimal digits. And that's a very clean interface between converting bytes into hexadecimal digits. Is that okay? All right. Okay, so we are almost running out of time. 2 more minutes. So we still got a little bit of time. On Thursday, what we'll do is we're going to look into memory itself, and then we ask, but how does RAM work? Okay, this is ROM. Okay, ROM is relatively easy to figure out. But how does RAM do it? Okay, in particularly, how can we overwrite the configuration of one circuitry and have it remember the new state and not to lose it? And then we can also retrieve it later on. Because that's the magic of RAM. Okay, ROM is pretty easy because everything is just written. It is all written in stone, so to speak, right? There's no way to overwrite it. So it's not really as intriguing as RAM, where you can say, oh, it used to have a content of 1, now I want to change it to 1. But once it changes to 1, unless you change it again, every time you go to that location, you retrieve the content of 1. So how does that work? Okay, so the next class is going to be focusing on just that. Okay, and not very surprisingly, I hope, it's a circuitry that can be made out of the 3 primary gates that we know: the NOT gate, the AND gate, and the OR gate. So through some very, very ingenious way of connecting the gates, we can have the smallest unit of memory called a flip-flop. So that's what we'll do on Thursday. And I'll be at the lab in case you want to do your homework assignment and have questions to ask. So I'll be there to answer your questions.
No demos though.
No demo this time.
Oh.